present to you in general what are VRW processors, what it means to be called a VRW processor. And then after some introductory slides, I will also then present basically the research work that I do in the computer engineering group that is surrounding VLW processors. We use the VLW processor as a basis. And for that processor, we developed multiple platforms that we use. And one of those platforms you will be experiencing during the lab. So that I try to explain to you what was the background of this design. It's not a straightforward design of a VLW processor, and explain to you what are the differences and how we believe that these are advantageous in the way that we design this processor. Okay? Any of you already know what the VLW processor is or have seen before? Anyone? Yeah? What do you think it is?
Well, he explained very shortly that it sends basically all groups of instructions at the same time that it can execute in parallel on the machine. Yeah. Then demands that basically the compiler does all the work.
Ah, okay. So you got the big picture already. Quite okay. So then I will not skip, but quickly go through a couple of keywords. Then maybe already Soren explained them to you. I just put them yesterday on the slide, so I have to read a little bit what I wrote down yesterday. Okay. So in order to get more performance out of the processor, of course, we would like to add more and more units in parallel, because the parallelism is not going to give you performance, right? Now, there are different ways how to do that, but physically, you have to put the units there, okay? Then it becomes a question of how do you then schedule the code in such a way that you can effectively use these parallel units. Okay? Now then you have basically these days two approaches, a superscalar processor or a VLW processor. Okay? Now you already alluded to the fact that with a VLW processor it is compiler based, so the way that you use these parallel units are via a compiler, so which explicitly says at what time what units should be used and how many should be used in parallel. So what is the other one? The other one is superscalar, is the one that most of us know. That's for example your RISC processor or whatever. And within that there's still two distinctions, in that you have a statically scheduled superscalar processor or a dynamically scheduled. What does it mean? A statically scheduled superscalar processor basically says, I look at the code and I consider it in order. Yeah, I never change the order of it, but based on the order that is being seen, let's say in the instruction window, you determine inside this instruction window how many instructions can be scheduled in parallel. But you never look beyond a certain set of instructions. You never take them out of order. Yeah? That's called then a statically scheduled processor. The other one, the dynamically scheduled one, is then, well, if in this window I can rearrange the instructions in any way without, how to say that? Without changing the functionality of the program and without violating the actual program, that you can also schedule them in a more complex way in order to gain more performance, being able to execute more parallel. But what is then the big disadvantage of that? The disadvantage of that is that you have to have a very complex or more complex instruction fetch decode unit with different window sizes in order to determine which instructions are really independent and which instructions are not independent, and which one you can therefore schedule in parallel. Okay? Like I said, so turning it around, that also means that for a VLW processor, you don't need such a complex hardware unit in order to schedule parallel code, but you do have to rely on a compiler to do it. Okay? So on the other way, for a superscalar machine, you do have an advantage in the fact that you can rely on dynamic code. That means while the program is running, while it's being executed, you have an instruction window, and this is dynamic. You know what the difference between dynamic code and static code, right? It's clear, right? Yes or no? Yes. Okay. Because dynamic is being running and static is fixed in code, right? Okay? Good. So you can gain some advantages from that, but it has to be measured. But if you don't have that unit there, you also gain in performance. Sorry, in power. Now, let me go through some characteristics. So, what is then the background of VRWO processors? If you really investigate where it comes from, you can trace it back to 1951. It was not called VRW at the time because it was called horizontal microcode. Everybody knows what microcode is or not? No, I see a lot of no's. Okay, so let me go to what microcode is. Let me give you an example. Let's say I would like to implement a certain function in the current day processor. Okay. And I cannot design a very simple single unit to implement it. What is then my choice of still to be able to implement this particular more complex function?
A controller.
Sorry?
A controller.
A controller. What does a controller basically do?
Tells it what to do all the time.
Yeah, so it contains a sequence of operations that emulates the functionality that I would like to do, right? Now, that emulation is precisely what is microcode, okay? So, you will then cut or subdivide your big operation that you cannot implement in a piece of hardware these days. You cut it into smaller pieces, and all of these pieces you can implement, yeah? So then these operations are called micro operations or micro instructions, yeah? And the sequence of operations is then called microcode, okay? That means when I would like to implement a certain instruction that you don't have, you microcode it, and then you can have the same operation. Is it clear, right? Now, microcode is not it's an old concept, but it's actually still being used, okay? It's even in current day processors, you will find microcode, and you find actually a lot of microcode still, because a lot of operations are being translated from complex operations into more simple operations. And there's even a concept of picocode, because sometimes even simple microcode is too complex to be implemented. And then you have picocode, which is another layer below. And then when I talk about picocode, it's mainly in the design of I/O. If you have to do I/O, it's a very complex operation that has to even go down to picocode in order to make it work. Now, then what is then, when you talk about microcode, there are two different versions. That is vertical microcode and horizontal microcode. What vertical microcode basically is, it says I have a certain instruction, micro instruction, and I look at the instruction and I decode it into what I need to do. So that concept of vertical microcode basically became RISC processors. What is then horizontal microcode? Horizontal microcode was that instead of encoding the operations in an instruction, I explicitly split them into multiple specifications. And that basically is then having explicit multiple instructions to specify, or actually at that time it was not instructions, but they were actually control signals that go to parallel hardware. Now, if you understand that horizontal microcode is the control, explicit control of parallel hardware, then I hope that you see the link between horizontal microcode with VRWs, because both have specific explicit instructions or control signals towards specific execution units. Yes? Okay, so that was a short intermezzo of microcode is. So yeah, so this one. So what we do in VRW processors is that We have a lot of parallel execution units, and you have to specify in your instruction word what you would like to do in parallel. Okay? And basically what will happen after it is that you will design a processor that fetches this long instruction words, and then you make sure that in each slot that you have in your instruction word correspond to a single data path inside your processor. Okay, so then you can go directly down, instruction, and then you have your execution data paths. Okay? Now, already said, in order to able to effectively use a VLW, you need to rely on a compiler. And if you do a straightforward compile, it's not always as very simple, not always easy to see that there's parallelism. Okay? If you just do a loop and you say, well, I do step 1, step 2, step 3, where's the parallelism, right? And that's why you have to rely on a lot of very sometimes complicated compiler algorithms in order to not only extract parallelism, but sometimes even construct parallelism in order to fill all the issue slots. Yeah? Okay, so now what are a couple of them? They are mentioned also in the book. So you have loop unrolling is a very common one, because the more you can unroll, the more code options you can have in order to find independent operations, and therefore you can schedule them in parallel. But software pipelining is another one. Is software pipelining familiar to everybody? What software pipelining is? No? Okay. A very quick intermezzo again then. Software pipelining is basically, if you look at the loop, you can see that there is that you can basically cut it like a pipeline into multiple stages. Okay? And so just look at the loop as an operation that you know how to pipelining, you know, right? Okay? So if you look at the loop, you can also say, well, this part of the loop is one stage, the other part is another stage, the other part is another stage, another part is another stage. It's like cutting pieces of code, right? Now if you do it right, you can also say later on, so it's like a pipeline, maybe I can visualize it for you. Yeah, so they hit all the interesting. Okay. I hope you can see it. So let's say this is a loop. You can also subdivide it into different stages of the loop. And then you can do software pipelining like this. So this is the next iteration. This is I plus 1 iteration. And something like this. I plus 2. Now in the same way that you understand pipelining, you can also start seeing the that you can also actually start executing different stages from a loop in parallel. Yeah? In this way, you can, of course, they have to be independent, but if you do correct, most loops like this, you can do it. Then basically I can execute different phases of the different loop iterations in parallel, and in this way you can actually artificially generate a lot of parallelism. Artificially. Yeah? And that's called loop unrolling, or it's also, it's called software pipelining. I thought I wrote another name. And modular scheduling is the other name for it. It's also called modular scheduling. Okay. I'm not going to yes.
Right. So this is in the where in the assembly, in the higher level?
In the compiler. So the compiler will look at the loops and then say, can I apply modular scheduling to it? And then basically investigates whether the different layers are independent, and if there are many iterations that you can do like this. This basically also means that if you start this at some point, let's say 3, so I reach the maximum here, if I assume 3. So this is then called your, I've forgotten the name now, but this is the preamble. because you have to set it up first, and there will be some correction at the end that you need to do in order to make sure that you collect all the correct results of the different loops. But this is what the compiler will do. Yeah? But this is just a basic concept of it. Yeah, and another interesting way to exploit PRWs in order to increase the parallel execution of it is doing predicated executions. Is predicated execution a terminology? No, not? No. So what is execution? Execution. Let's say if I look at the very simple if statement, then you have if something is true, then you do something else, you do something else, right? Very simple if statement. Okay. Now, if you implement this very straightforward way and you don't do anything optimization to it, that means I have to evaluate something, then do that and do a jump. Or if that is not, if that evaluation is not true, then jump and then do something, right? Because that's how it will look like. Now, what is predicated execution? Predicated execution is that, well, why not do both then statement and else statement at the same time? Because these are supposed to be independent. And then at the end do a compare and say, okay, which one should I have taken? So in this way you can create that you execute both, but you always have to check afterwards which one it should have been. Yeah, so then the check is not before, but the check is after. And you can predicate instructions saying, okay, these instructions you never commit until I have checked that it's correct. Yeah? But you can still perform the operation. Okay? Now, this is one way to improve parallelism, but personally, in my opinion, I find it a bit weird in the sense that your processor is being kept busy, but you might be throwing away half of the work that he has done.
You will. Sure.
Yeah, of course, because that's predication. So in that sense, in my opinion, it doesn't sound right. Okay? So this is already a way to go to my research later on, but we do it a different way. So that's why I say it like that. Okay? Now, and then I can sum up a lot of disadvantages of using VRW processors. And these are the main reasons also that you don't find them in your laptops, in your desktops, or whatever, but you do find them in all your mobiles. Yeah? Every mobile has a VRW processor. I'm 100% sure of it. Because usually those are the processors that deal with all the network processing. Yeah? Because if you know your algorithm well, and you know that there's a parallelism in there, you will use a VRW processor because it is more power efficient. Because if you know exactly what he needs to do, you can fill all the slots, and then you don't need complicated instruction fetch decode units, because these fetch, depending on the complexity that you actually put in there, you can also do register renaming, out-of-order execution, and whatever, predication, and keeping track of all of this in order just to improve the parallelism of a superscalar machine can consume quite a lot of power. And then I'm not talking about 1 or 2%, but it can also actually go up to tens of percent of what your processor is actually burning. Yeah, just in order for you, because keep in mind the code that the processor that you send to a superscalar processor is sequential in nature. Yeah, is sequential code. It's not parallel code. Yeah? That means he needs to do a lot of work in order to extract parallelism. And with the VRW processor, the compiler already told you if you execute it like this, it is parallel. You don't have to do anything else. Yeah? That's why you see a lot of them in DSPs. TIs are very common, but STMicro DSPs that deal with GSM or other networking protocols. There you will find very common, a lot of PLWs. Now let's go through a couple of disadvantages of PLWs, the reason why they're not on general purpose, as we know. The thing is that with the VLW is that you specify already beforehand what you want to execute. Okay? And usually what you can do is in each data path you say this data path can do branches, this data path can do integers, this data path can do floating point or this. So the functionality of each data path is predefined, and what you do not want, of course, is to have each data path be able to do everything, because you will not use everything, therefore a lot of is going on. Yeah? So you would like to pre-specify what each data path can do, which is a limited set of your instruction set that you have. Okay? Now already this choice ensures that I cannot turn any program to fill all the slots all the time. Okay? In the same way that the superscalar processor also cannot fill all the slots all the time. It tries its best, but cannot. So therefore, but the problem is that in a VLW processor, you have to be a little bit more explicit in saying that there's nothing being scheduled. Yeah, so you have to insert knobs. These are no operations. Yeah? So you have to insert no operations into the code and say, okay, don't do anything in this data path because I could not find anything for you to do. And therefore it can happen that code can contain a lot of knobs. Yeah? And then I'm not talking about, again, 1 or 2%, but depending on the application and the mismatch between application and the VLW that you've chosen, it can go up to 90%. Yeah? That means 90% of the code that you send to the processor says, don't do anything. Yeah? But still, this don't do anything, these knobs, you need to store. So that means another thing is that it explodes also your code size, yeah? Because you have to store it. Now, of course, knobs is if they're so common, they will of course find ways to reduce the code size. And one way to do it is to do simple compression. Yeah? You do compression. You say, oh, there's so many knobs, and you find smart ways to not store them. Okay? Now there are different ways to that, simple encoding, but you can also have things like stop bits. So you say, my instruction word only has 2, then I say, I put a stop bit here, that means the rest are knobs. If the rest are knobs, I don't need to store them because there's a stop bit there. Okay, so when you decode it like this, stop bit, go to next word. The next is the next word. Okay? So there are many different ways in order how to deal with this problem. Now, if you don't deal with it, another thing is that the fact that you have to store them somewhere at some point. Yeah? Okay? I can encode them and not store them in hard disks, but at some point I need to send the knob into the processor. Yeah? So there is a stage somewhere that this knob has to appear. Okay? Now, if you appear, there are different choices, but some people have chosen to do the decode stage, the knob decoding, before they enter the cache, and some have chosen to do it after they between the instruction cache and the processor. Yeah? Now, if you do it before the cache, that means I have to store the knobs in the cache. Okay, and if you do it after, that means I have to decode them in the short time that I have between the instruction cache and the processor. So there are trade-offs in what's best. If you have chosen for the first one, also literature tells us that these days instruction caches can consume up to 50% of the power that is being consumed by the processor. Okay? And if 50% of the power is just to store knobs, it's another way to waste power, because it's just wasted because you are storing things that you don't want to do. Okay? Now, again, in my own research project that I'll describe it later, I'll tell you a little bit how we deal with this, and in order to reduce the number of knobs and save power in the instruction cache. Another problem is that with code compatibility. Now, if you say, well, my code, so let's say I make a design, and the design says I have 4 data paths, and each data path can do this and this and this. You will schedule the code to put those specific instructions in those issue slots, right? Now, let's say I go to the next generation of my processor, and I change the data paths. So that means I can no longer use the old code, because the old code says in data path 1 I want to do an add, which no longer exists in the second generation. It's possible. Okay? So code compatibility has always been one of the main bottlenecks, yeah, or Achilles heels, or whatever you want to call it, of VRWs, because yeah, it's very limited in how to do that. So then you need recompilation, and there's always a debate between I forgot the English word. People that are against something and people are for something. You call them opponents and proponents, right? Proponents, correct word or not? Yeah, okay. So proponents and opponents of the VRWs, they always have this debate and say, okay, because the proponents of VRW say, well, if I schedule code, if I take code from, let's say, x86 from 1980s and I run it on the i7 these days, they will also not be efficient, right? Because the i7 contains a lot of optimizations, and actually if you read the manual correctly, the ISA book, it tells you not to use certain things. Yeah, of course those things can still exist in the 80s code, the legacy code that you have, and therefore it will not run always efficiently. So the proponents say, in order for me to use the i7 also efficiently these days, I need to recompile my code. Yeah, so therefore the VRW guys say, well, it's the same for VRWs. If you want to use more efficient the current generation of VRWs, you have to do recompile. But of course, another point that is a bit missing here is that the 80s code can still run on the i7, but slow. But if you take very old VRW code and you go to the new generation, it cannot run. Yeah, so that is, what do you want? Huh? Another disadvantage of VRW processors is that if they're very small, this is not a huge problem. But the moment they become wider and wider and wider, if you want to have more and more parallelism, even the topics that I discussed before are becoming more and more bigger, let's say. But also the pressure on the register file is becoming a huge issue. And why is that? It's because if you look at current days operations, they usually have 2 inputs and 1 output, right? Like add 2 numbers and you store it, right? So 2 inputs, 1 output. That means that for each slot in my VRW processor, I need to be able to read from the register file 2 operands and be able to write 1 result. Now, if I have a 2 write, I need 4 read, 2 write. If I have a 4 write, I need 8 read, 4 write. If I have an 8 write VRW, I need 16 read and an 8 write port register file. Okay. Now this blows up exponentially in terms of area, because the more ports you add to register file means the more you need in order to get out and to be able to write it. So it explodes exponentially. Now that is also in holding back VRWs also, because you want to actually build as wide as possible, but now there's actually another solution for this, and the solution is called VRW clustering. Okay? What basically then happens is that I split my register file into 2 parts, let's say. Yeah, and then I have 2 base parts that connect to it. Yeah. So it means this is one way to build a four-way VRW. If I have a single register file, I need all the lines to connect with 1 file. Therefore, I have 8-bit 4 write ports needed. But if I cut my register file in half, I only need per register file 4 read, 2 write ports, which is much smaller. Okay? In this way, you can reduce the size that you need in order to design the register file. But the problem is that if I would like to access a register that is on the, let's say, the lower half of my register file, because now this is, for example, numbered register 0 to register 31. This is now register 32 to register 63. There used to be in a single register, yeah? But now I cut it in half. By cutting it in half, I have much reduced number of ports per register file. But if this part of my processor, this is called a cluster, so cluster 0, this is then cluster 1. If he wants to read something, let's say a register here, then there must be an explicit, no, sorry, it's incorrect. There must be a copy operation. Yeah? He must send a request to this part, this cluster, and say, I want to read this register. And then this register needs to be put somewhere to be able to be consumed, let's say, by your data paths there. Okay? Now, there are explicit copy operations. Explicit copy operation means that inside the code, yeah, there is it says, I want to read from cluster 1 this. So that's explicit. But you also have implicit copy operations in which the hardware detects that you want to read register, let's say, 40, and he knows that register 40 is not in this part, and then you will implicitly go fetch register 40. Okay? But another thing you have to keep in mind is, of course, is that the execution of these 4 data paths must still be in lockstep. Yeah, because you still have to maintain the correct independence or dependence of the instruction that you have that you're executing. Okay? That's lockstep. Lockstep is then that the data path that I have needs to be executed in lockstep. So the next instruction, next instruction, next instruction. And that basically also means that, let's say there may be a load operation and then it causes a cache miss. That means I have to hold every operation to wait for one of the data paths to be able to fetch data. Okay? Now, also in the project that I'm running, we also deal with this, but we deal it in a different way because we just say we do a context switch the moment that cache misses. Yeah? So assuming that I run multiple applications at the same time, and the moment that one misses, you just go to another program. And then you can keep on working, and then so on. I'll go to the
I have a question.
Yes? Sorry? Yeah.
When you experience miss in the cache,
Yeah.
and a number of applications are running, and
Yeah.
you said you do context switching.
Yes.
But there is always overheading more than context switching. How do you
Yes.
manage that?
Okay, that's a very good question. Because context switching, basic context switching, means I have to store the state. The state needs to be stored in memory, and then load the state from motherland. Okay. There are other approaches in which what you can do is I can have something like multiple register files that I put inside my processor design. And the moment that I switch, it's just switching to another register file.
Okay. Like Windows, like window.
Yeah, something like that. You could see it as a window.
Window of registers. You just shift the window.
Yeah.
Something like
Yeah, it's like then I have something like a register file. So register file. But then I have, let's say, 4 of them. And this belongs to thread A, B, C, and D. So the moment that program A misses, I just have a selector here that selects which register file to take. Of course, if I have more programs than 4, you need the mechanisms to deal with that, but then it's an interplay between either a runtime system or an operating system that then knows exactly what contexts are inside the processor and then do the correct job in switching which one out. Okay. Well, actually, we have another nifty idea, not about multiple register files, but another idea that I'll explain when I talk about my own research, in which we can switch programs, actually not switch programs. Let me describe you another scenario. A multi-core scenario. And that's a very simple picture. Let's say I have most of you know what Big Little is, right? Have you heard of Big Little? No? The Big Little concept is the ARM processor that you find in your mobiles that says I have big cores for complex processors threads and little cores for simple threads. And then what you then do is that if you have programs that are not needing a complex core, you just run them on a smaller core or you switch between them. Okay? Now if I then have a program and I run them on the 4-way core, yeah, and I would like to switch them to be able to run on the other core, what you then need to do is you need to interrupt your execution at some point. Okay? You need to take the state in the register file and other whatever status bits that you have, and then move them here, and then you can continue execution in the other core, right? Now, the thing is that we made a design, something like this, that has a single register file. Actually, it's not 100% true. It has 2 register files. Yeah. And then you have something like this. So I still have these 2 cores. If I run this program on this core, it's connected like this. Okay? So I run it. And the moment I say, okay, I don't need all the power or all the capabilities of this core, I would like to switch it to there. So I interrupt it, and I say switch, and I do this internally. Okay? That's basically what happens. It's not exactly drawn, exactly the way that I'm drawn here, but that's basically what happens. So in this way, I don't have to take the content of the register file out, let's say through my caches or whatever, and then move it back in, because that takes a lot of time. Yes?
But can you still load the core simultaneous?
Yes, because I have 2.
So that's all.
Yeah, so I can still run 2 threads at the same time. Yes?
Who controls all this? The interrupts, the transferring?
Smart design. Yeah, you have to be aware of this. So we're designing this now. So we are now doing a very initial, we have a design that can work like this. And we are now trying to build a runtime system that can, of course, you need to issue control signals.
Yeah,
in
well, I
order
mean,
to do that.
is it the compiler that has to manage this? Or
No, the nice idea about this is that the compilation that we have is the same for both programs. So that's what something we call the generic binaries. It's a way that we compile the program so that this program can run in 4-way mode. So this is a 4-way VRW, and this is a 2-way VRW. And it's exactly the same code that we run. And so since I run exactly the same code, this is stored in my iCache. Yeah? And this one basically sends the code there or there. But it can also send 2 at the same time because I can run 2 programs at the same time. Okay? And we do have a demo of this. So if you're interested in looking at how this particular design works, you can come up to the 10th floor and I can pinpoint you to a PhD student of mine that can fire up the demo in 2 minutes, and then you can see how we do it in context switching. So basically he issues an interrupt here, And interrupt tells the control hardware to say, okay, now I've moved that to there, and then without doing a context switch the traditional way, it just makes this switch and it runs. Okay? Any questions on the VFWs in general? Then I propose to have a break, and then I will tell you about my own research. Okay? So I'll go into more other slides.